And now what we want to do is, let's find the mass of liquid that occurred. So if we do the mass of liquid, it's Ma times the difference between omega 1 and omega 2. So this refers to the water vapor, and the difference between the water vapors is the amount that's been condensed. So Ma 3.269 times 0.04 minus 0.0088. We're going to have this is 0.102 pounds mass. And MV2 is equal to 0.131 minus the liquid 0.102. So the mass we have, the vapor we have final is 0.029 pounds mass vapor. So we started out with this amount of vapor, we condensed this amount, we're left with that amount. And that's basically what we have. And so I could also do that MV2 is equal to MA times omega 2. So either way, you'll get this, you'll have the same result. So now, let's do the first law analysis where we find out what Q is. So, well, what I have written down here was a closed system, and we have this mixture. So the first law for a closed system, Q is equal to delta U plus W. There is no work done because it's a constant volume problem, and we have, so this is equal to U2 minus U1. U1 is equal to U of the air plus U of the vapor. MA UA plus MV UV. I have to put the masses in, I can't do it on a unit mass basis. And U2 is equal to MA UA2, because I should put it here, plus MV UV2 plus ML UL2. And so now what we want to do is we'll just substitute in these values in for air. I have that U is equal to C sub V T, and for H2O, U vapor is equal to U sub G. So I've got to be able to look those up. So anyway, U1 is equal to 3.269 times C sub V, 0.1714, times 570, plus 0.131 times 1046.7. So this is U sub G at 110 degrees Fahrenheit. And this, if I add these together, this is 456.5 BTUs. So this term is 319.4, and this is 137.1. So we see that the major part is the air, but this contributes significantly to the total. For U2, we're going to have liquid in there as well, so it's a little interesting with U2, and we'll look at what those values are. I'll give myself a little more room and start over here with U2. So U2 is equal to 3 0.269 times C sub B 0.1714 times 510 degrees Kelvin plus 0.029 times 1027.2. That's U sub G at the lower temperature, plus 0.102, the mass of the liquid, times 17.7, and this is U sub F, and this is U sub G. So if I multiply these terms out, this is 285.7, 29.8, 1.8. And we see, so what's going to happen in practice is sometimes we don't pay attention to this because it's so little in the scheme of things. And so this turns out to be 317.4 BTUs. And then Q is equal to delta U is equal to 317.4 minus 456.5 is equal to minus 139.1 BTUs. So the heat that left, so the heat, Q, was minus, indicating it was leaving, 139 BTUs. There's one more topic that we briefly want to mention here, and it's called adiabatic saturation. We're not doing calculations with it, but we will be using this concept in the chapter where we look at air conditioning processes. And so I would like to look at adiabatic saturation. And basically, we're going to introduce the topic of dry bulb and wet bulb temperatures and what that means qualitatively so we understand it. And these are used when we get to chapter 16. So if I take a stream of air, I'm not going to have it go into some chamber. I'm going to have this. I'm going to have water here, H2O. I'm going to have it state 1. Phi is less than 100%. Here, we're going to have its Phi is 100% and it's saturated. And so what happens is we have the air go over this water, and as it goes over the water, it picks up water vapor. So we have it picking up water vapor. And let's look at this on a TS diagram. So if I look at this on a TS diagram, state 1, state 3, this is our PG. So if I look at this, I have this, and so we know that this is the dew point. So that's the dew point. T1, dry bulb temperature. So if I just put a regular thermometer in here, so if I put a thermometer in here and measure the temperature, that would be T1. So I'd be doing that. And now what happens is the water evaporates. The energy to cause evaporation comes from the enthalpy of this term. It's a constant enthalpy process. So it's a constant H process going on. And I'm looking at something that goes here. And we'll call this state 2, which is what we are here. So we're at state 1 and state 2. And at state 2, it's the adiabatic saturation temperature. or T wet bulb. And so we'll be using this concept later on. It isn't something where we're going to do calculations with now, but it's something that we want to understand conceptually for later on when we do HVAC work. For homework, which I nearly forgot. And here we're going to be doing this part in English units. So we have 11.11 star, 11.21 star, 11.23 star, asterisk rather, whatever, 11.25 star, and 11.29 star.